Okay, I think we're up and running. So I wanted to make a video that talks about the concepts of sensitivity. And as we've mentioned in class, sensitivity, this is the ratio between some input and some output. We'll have output over input. So I might have some pressure input that's causing some moving part to deflect, and that will create an electrical output. So we'll have, let's say, pressure as the input, and then that will produce some voltage output in the electrical domain. And as we'll see as we get further in this class, that we can try to derive the relationship between the input pressure and the input voltage, or the input acceleration and the output electrical signal, or what have you. I might have misspoke there. Input pressure, output voltage. Now, the general idea, and we'll do this just looking at a vibrating system, is that we can write a differential equation or some model and then solve for the ratio of the output to the input. So if we just look at the mechanical domain only, we might have a force as an input, and that will produce some displacement as an output. So let's go ahead and look at a spring mass damper system. We have some mass, some stiffness K, and some damper C. And I'm going to pull on this mass with some force. And that force is going to cause this thing to move at some amplitude or some rate of displacement x of t. So the force is changing as a function of time, which is going to cause the position of the mass to change as a function of time. So if we were to do Newton's second law on this, Newton's second law says that the sum of forces acting on the object is equal to m times the acceleration, which I will write as the second derivative of x. So that's x double dot. And if you were to draw the forces that are on this mass, you have f of t going to the right. And then if this mass moves to the right, you're going to have the spring force trying to resist it, and the damping force also trying to resist it, where the damping force is dependent on velocity, not on position like the spring is. So if we sum these forces, and again, we're assuming this moves to the right, so we'll say that this is our positive direction, we will have f of t minus kx minus cx dot, that is equal to mx double dot. And then, of course, we can get everything up to one side to give us our differential equation that relates our input to our output. Now, what we would like to do is solve this differential equation, or at least try to solve for this ratio of output to input. And the simplest way of doing this is to use Laplace transforms. And you can go look at a table for what the Laplace transform are. But if we assume steady state, which means we're going to neglect any sort of initial conditions, meaning no initial conditions, our Laplace transforms are pretty easy. So I'll just make a table real quick, because remember, we're going from the time domain to the S domain, or the frequency domain. If you have x of t, the Laplace transform becomes x of s. If you have the derivative of x, we have x dot of t, we'll have the same x of s, but we will also have a factor of s in the front. And then similarly, when we get to the second derivative, we'll have two factors of x in the front. And note, there are other terms here that you would subtract off from those first and second derivative terms, but if we assume no initial conditions, they go to 0. So that's what we got. So if we take the Laplace transform of both sides of this, we will get ms squared x of s plus cs x plus k x that is equal to f of s. Remember, this is f of t originally up here. And now we're converting to the frequency domain. That makes it f of s. And I want to solve for the ratio of output to input. And the output is x. So let's factor this out of the left side and say that this is equal to f of s. And I want to solve for output over input. X is the output. So I want to solve for output over input. And again, these are both functions of s. And if I do that algebra, I will get 1 over ms squared plus cs plus k. And this is what we'll call our transfer function. That relates the output and the input. Now, we have to note that S is a complex number. S by definition is j omega. Now, there is a real part of that, but we're going to neglect that for this. We're just going to look at the steady state and think about what happens at different frequencies. So what we'll do is we will substitute j omega into the transfer function. So I will do x of j omega over f of j omega, and we'll go ahead and plug that in. For S. So I'll plug it in for S. I'll notate that with red. We'll get 1 over m j squared omega squared plus c j omega plus k. And then since j is the same thing as I, mathematically speaking, this is the square root of -1. J squared will be just -1. So again, this term, that is going to be -1. So this will be 1 over negative m omega squared plus, and I'll put the j in the front here, j omega c plus k. And this is still the transfer function, but now we have it in terms of frequency. Another name you might hear for this is the frequency response function. Or the FRF. As that relates the input and the output, and we can see what that input versus output looks like as a function of omega. Now, this whole thing here, this is a complex number or an imaginary number because of this j. And if we have something that's complex, there are two things that are buried inside of it. First, the magnitude of the complex number is buried inside. And this is the ratio between the input force and the output displacement in this case. This is the ratio of output over input. And two, the other thing that's buried inside of the complex number is the phase difference between them. And that's due to the presence of the damper, phase difference between the input and the output. So for example, maybe I have my force. Let's say this is my force. My force is sinusoidal. And at a particular frequency, maybe the displacement's a little bit behind it. And when I say behind, it looks like it's in front of it, right? I mean, just looking at it to the right. But if you think about this in terms of time, this might be 0 seconds, this might be 1 second. So when the force starts to go up, the mass doesn't move necessarily until a second later. It's a second behind. This is 1 second delayed. And that's also buried inside of the transfer function of the frequency response function. For our purposes, for what we're talking about at the moment, we want to look at the sensitivity, which is related to the magnitude, or which is the magnitude of the complex number. That is our sensitivity. So let's go ahead and look at this complex number now. I'm going to go ahead and copy and paste this from up here. And what we're going to say is that S, the sensitivity, I'll do capital S to not get confused with the little s's in the Laplace domain. This will be the magnitude of x omega over f of omega, which will be the magnitude of this fraction. Now, as we discussed in class, the magnitude of a fraction can be rewritten as the magnitude of the numerator over the magnitude of the denominator. Let's think about the concept of magnitude for a second, because we give you this equation of the square root of the real part squared and the imaginary part squared. Let's just understand where that comes from. If you were to plot this in the real imaginary plane, let's go ahead and let me come up with an example here. Let's say I do z, some complex number is 3 plus 4j, or j4. What that means is, if we were to plot that on the real imaginary plane, remember that the x-axis is just the real component of the complex number. So in that case, this is 3. And then the up and down on the y-axis is due to the imaginary part. So that'll be 1, 2, 3, 4. And we will see that this is how we plot that complex number in the complex plane. And we will draw a vector that goes from the origin to that location. Now, if we were to draw a right triangle here, we will see that this triangle is the length of it, or the angle of it, depends on those complex numbers. So I can say that this side here, that is 3 from the real part. And that side there is 4 from the imaginary part. And the magnitude of z is the length of the vector, which from Pythagorean theorem will be the square root of 3 squared plus 4 squared. In that case, this is 5. So that tells us what the magnitude of the complex number is. Additionally, if you were interested in the phase, that would be the angle that the vector makes with the x-axis. And that'll just end up being, from geometry or trigonometry, the inverse tangent of opposite over adjacent. So to generalize this, the magnitude of some complex number is the square root of the real part squared plus the imaginary part squared. And then the phase is the arctangent of, now is it the imaginary part or the real part? Well, we see opposite, that is on the y-axis, that is our imaginary part over our real part. So now let's go ahead and use that concept for here. So let's look at this expression again. I'm going to copy and paste this again. We'll bring it down lower. So we have the magnitude of 1 inside of the numerator. And at the numerator, if we were to plot that in the complex plane, let's just show that. Again, this is real. This is imaginary. The numerator is just 1, and that's just a real number. So the length of that vector is just simply the value of the real part. So for this case, this is just 1. So the magnitude of our numerator is 1, and then what we'll do is divide by the magnitude of the denominator. So we see we have some real stuff here. This is real, and then this is the imaginary stuff, the omega c. So this will be the square root of the real part, negative m omega squared plus k squared. Remember, coming back up to here, plus the imaginary part, which is omega c. Note that the j is not a part of that. The j just tells us, oh, that is imaginary. It's the part that is associated with the j, because you see here, this length is 4 in the j direction. That length is not 4j. That doesn't really make sense physically. We just have to note that, because that'll change things dramatically if you include a j here, because then I'll end up squaring it, and I'll bring a -1 and so on and so forth, and that's a problem. This is the sensitivity in between the input and the output. And it depends on the dynamics of the system. So what is the spring? What is the mass? What is the damper? And it depends on what frequency the input force is changing at or is oscillating at. So let's look at some cases. Let's say we look at low frequencies. Maybe omega is equal to 0. If we were to have this spring mass system, and this force in general will be something like some amplitude sine of omega t, or let's make it cosine. And I have f naught cosine omega t. If I plug in a low omega, maybe omega is equal to 0, this will just reduce to f naught, just some constant force. And if I have a constant force acting on this, we will see that the mass will displace a little bit to the right due to that constant force. So we see that it's gone a little bit to the right, that's x. And the amount it displaces, if we assume it's just static, is based on the stiffness. We know that f is equal to kx, so the amount that it displaces, or rather, if you look at the input versus the output, we'll see that x over f naught is 1 over k. Output over input, you have a static force that's not oscillating or not changing. You'll just get 1 over k. Now, if you come to the transfer function up here, and if we plug in omega is equal to 0, we'll see that our sensitivity is 1 over the square root of, if we plug in omega as 0, we get 0 plus k squared plus 0 squared. We just get 1 over k, which matches our suspicions from vibrations. If I'm just pulling on something with no sort of going back and forth, no sinusoidal input, just strictly the force pulling on it, we know the relationship's dependent on the stiffness. And we see here that the sensitivity is 1 over k. And what we'll do is assume that it's 1 over k for low frequencies, not just 0, approximately 1 over k. So if I were to draw a graph of the sensitivity, okay, let me go slower, draw a graph of the sensitivity as a function of omega, we will see that for low frequencies, we will have a value of roughly 1 over k. And that's not perfect. Obviously, as we get to higher frequencies, that 1 over k approximation will deviate. But for our purposes, that is good enough. Okay? In terms of vibrations, if we have this spring mass damper system that is now being excited by a sinusoidal force, the system has its own natural frequency that it is excited about. That is what its happy place is. That is what's omega n. That's the square root of k over m. And if we were driving the system at this frequency, and again, it's not exactly at this frequency, it depends on the damper, but let's assume it's lightly damped, we'll see that we will have maximum displacement because of the fact we are exciting the mass at the frequency that it wants to move in. If you think about a swing set, if you're swinging on a swing, if you were to pump your legs at the right moment, that allows you to have a greater height. Now, if you were to pump your legs at a random point in time, your frequency of your pumps are different than the natural frequency of the swing. And because of that, you won't have a lot of displacement. But if you are exciting the system at its special frequency, you will end up getting a lot of deflection. So around that frequency, we will get a max deflection. Let's see what that looks like. So again, if we were to go to our, let me not use this. Let's get this back down here. So if we were to look at the sensitivity now, and what we'll do, we will assume that the driving frequency, which is omega, we'll assume that this is equal to omega n. So you can get a feel for what this does at that frequency. So let's plug that in. We'll get 1 over the square root, and don't forget that omega n is the square root of k over m, which means that omega n squared is k over m. So we get negative m times k over m plus k squared plus, if I were to square that term out, I would get omega squared c squared. So I'll just write this as k over m times c squared. And what you'll note is that this term here will end up going to 0. If we just go ahead and look at this on the side or something, we will have negative m times k over m, which means that those k's will, the m's will cancel, plus k, that ends up being 0. And then we will have 1 over the square root of k over m times c squared. And I guess I didn't really need to put in omega n to the second term, because all we're going to end up seeing is that this will just become 1 over, if I separate the square roots, I would just get 1 over c omega n. And this is my sensitivity when the driving frequency is equal to the natural frequency of the system. And we can reduce this in a bunch of different ways. For example, if we note what the damping ratio of the system is, we go back to vibrations, we know that the damping ratio is C over 2m omega n. So we can go ahead and do some manipulation here. Maybe we solve for omega n or C or something along those lines. Maybe we'll solve for C. C is 2m zeta omega n. So we'll go ahead and plug that in to this C right here. You will get 1 over 2m zeta omega n times omega n. So this will give us 1 over 2m zeta omega n squared. We already know what omega n squared is. That's k over m. What we'll see is that these ends cancel, and then I am left with a sensitivity of 1 over 2 zeta k. And by definition, this 1 over 2 zeta is the quality factor of the system. This ends up being q over k, where q by definition is 1 over 2 zeta. So depending on the value of Q, we will see that as we approach the natural frequency, we will end up going up to some peak value and then ultimately dropping, where that peak value, that guy, to that point, I'll draw dash lines, to this point, that is going to be Q over K. So depending on the quality factor of the system, that'll dictate how high a peak you have. If you have no damping, so if zeta is equal to 0 because there's no damping at all in the system, what that means is that Q goes to infinity, right? Because Q is 1 divided by 2 zeta. Zeta 0 will jump up, which means that our peak will go all the way to infinity. Which basically means that if you go and oscillate the system at its natural frequency, you will have a huge response, massive response. With damping, it minimizes that response because we're taking energy out of the system. The last thing now is what happens after omega equals omega n. Again, that's where resonance occurs. I should probably write that down. System has no natural frequency. We're driving at resonance, which is why we have this massive displacement when you're resonating something. Now let's say that the driving frequency, now assume that omega is very high while omega go to infinity. And if you take the limit as the sensitivity goes to infinity, you'll see that all of these omega squared terms blow up, which basically says that our sensitivity is 0. And that is, again, the ratio of the displacement to the force, which means that no matter what the magnitude of the force is, if the frequency is very high, we will see that the displacement is 0. And again, let's picture this. If I have a mass and I have something that is going back and forth, so this force is changing direction a lot. Maybe I'll draw a picture of me like pulling on this or something. Imagine I'm pulling on it, and then maybe there's someone else on the other end that's pulling it in their direction. So they're pulling this way, and I'm pulling this way. I pull to the right, the other person pulls to the left. I pull to the right, the other person moves to the left. And it's going back and forth. Now, if we try to move this very quickly, I'm going right there, going left, and going back and forth, right, left, right, left, right, left, right, left. We'll see that the mass will basically stand still. It doesn't have time to move. As an exaggeration, imagine that I'm pulling on this mass for a minute. I'm just constantly pulling this thing to the right for a minute. And then after the minute, the person on the left goes, and they go for a minute. We'll make some progress. That mass will move to the left or to the right. But now if I only have 30 seconds to move it, I won't move it as far. And then the other person has 30 seconds to move it. They won't move it as far. So I'll be moving it back and forth a little bit. Now, instead of 30 seconds, imagine I'm moving it 1 second. So I move it for 1 second to the right. The other person moves it for 1 second to the right. And we're just oscillating back and forth. I'm going right, they're going left, back and forth, back and forth. The mass basically stays still due to the mass's inertia. It stays still. At high frequencies. And that's why if we come back up to our graph, we'll see that as we go the higher frequencies, this will just go ahead and drop to go to 0. So this region is stiffness dependent because the low frequency is the only thing that's thing is the stiffness, basically, the K. Over here, we say that this is damping dependent because the height of that peak depends on the damping in the system based on Q, which is 1 over 2 zeta. And then over here, we have what is mass dependent in the system, because we know that at high frequencies, the mass does not have the ability to move as far, and therefore our output displacement is low. So no matter what the input force is, if it's oscillating at a very high frequency, then we'll see that it doesn't have a lot of movement. And our output displacement being zero means that our sensitivity is zero. I hope that this is a decent review explaining the concept of an FRF. To sum it up, at least for our purposes, we want a sensitivity that's relatively constant, ideally constant when we're designing a device. So we will go ahead and look in this region as the region that will be our bandwidth. And that's something I'll talk about in a future video. Okay, hope this was helpful. Thanks.